Muruganandam. I am working as an associate professor in the Department of Mechanical Engineering in Ph.D. College of Engineering and Technology. It is the lecture 1 in the series of lectures on computational fluid dynamics and heat transfer. This lecture 1 is going to deal with governing equations of fluid flow. Today on 15th July 2025, I make this lecture 1 on the topic governing equations of fluid flow. The fluid dynamics and heat transfer. The objective of the study of fluid dynamics is to find the quantities called lift forces and drag forces on the bodies, such as aircraft, where the weight of the aircraft is acting downwards. Against that weight of the aircraft, a force needs to be applied on the aircraft to lift it above the ground level. So that lift force on the bodies. Again here, the drag forces in the aircraft when the plane is moving in the forward direction, where thrust force is acting against that forward motion of the aircraft. Due to the airflow, there is a drag force acting on the aircraft. Similarly, when the ship is sailing on the sea, the fluid friction, the water, due to water, acts in the direction opposite to the direction of motion of the ship. That is another example of drag force on the body. When the automobile is moving forward due to the thrust force given by the engine, IC engine, against that force there is a resistance force due to the motion of air is drag force acting on the automobile. So these are the examples for lift forces and drag forces on bodies. To find out these quantities of engineering interest, these are the quantities which are interest for an engineer. We study the fluid dynamics, we analyze the bodies and the flow around the bodies using fluid dynamics principle. To find out the heat transfer coefficient of the surfaces, we study the heat transfer on the bodies. In order to find out these engineering quantities which are of great interest for the engineers, it is required to find the velocity distribution inside the flow. For example, a pipe flow is shown here where the velocity distribution is also shown. The velocity is 0 at the pipe surface. Due to the no-slip condition, the velocity is maximum at the center line of the pipeline. The velocity varies from 0 at the pipe surface to the center line of the surface. So this kind of velocity distribution, velocity variation within the fluid flow is called velocity distribution. Pressure distribution, there is a variation of pressure acting on the bodies. For example, the airfoil, the section of the wings of an aircraft is shown here. The differential pressure force which acts on both the top of the airfoil and bottom surface of the airfoil results in a net lift force acting in the upward direction. So the pressure distribution, the variation of pressure at various points along the surface of the aerofoil. Temperature distribution. Here a pipe is shown where the two pipes are joined using welding. Within the welding joint, the temperature varies from root to the outer periphery. So the way in which the temperature varies is called temperature distribution. Similarly, density distribution inside the flow. So to find out the quantities such as lift force, drag force on the bodies, heat transfer coefficients of surfaces, which all will indicate the performance of the bodies, performance of the engineering devices. These are the performance parameters. We can also say performance parameters. In order to find out these performance parameters, we need to find out initially the distribution of the velocity, pressure, temperature, density inside the fluid. The velocity distribution, pressure distribution, and temperature distribution and density distribution, these variations are found out using the theory of fluid dynamics and heat transfer. Computational fluid dynamics and heat transfer. The procedure of computational fluid dynamics and heat transfer, abbreviated as CFD-HT. It starts from the general equations governing the fluid dynamics and heat transfer. For a person who has to get expertise in the field of computational fluid dynamics and heat transfer, first of all, he or she must have knowledge about the arrival of these equations from the basic laws of nature, such as conservation of mass, conservation of momentum, conservation of energy. We have to arrive at these equations governing the fluid dynamics and heat transfer. Based on the given problem on fluid dynamics and heat transfer, these general governing equations are reduced into simplified form of governing equations. These simplified forms of governing equations are discretized into algebraic equations. Either the finite difference method or finite volume method or finite element method can be used to discretize the governing equations, which are in the form of algebraic equations. These algebraic equations are solved to arrive at the results. That is the entire procedure of computational fluid dynamics and heat transfer. As I have already explained in the procedure, the first step in the computational fluid dynamics and heat transfer procedure is to arrive at the general equations of governing fluid dynamics and heat transfer. So that is the topic for today's lecture 1. I am going to arrive at the general equations governing the fluid dynamics, such as continuity equation and momentum equation. I shall also use these equations to arrive at a reduced form of the equations for a given problem. The general equations of the motion, fluid motion, are either arrived in differential analysis procedure or integral analysis procedure. Here I am going to explain the differential analysis procedure. The conservation of mass principle when it is applied to a control volume, which is a typical volume selected from the fluid flow domain, is as follows. The time rate of accumulation of mass inside an elemental control volume is equal to rate of inflow of mass minus rate of outflow of mass plus rate of increase of mass due to a source inside the control volume. So that is the conservation of mass principle which is applied to a control volume inside a fluid flow. The law of conservation of momentum, when it is applied to the same control volume, it is stated as follows: rate of accumulation of momentum inside an element of the control volume is equal to rate of inflow of momentum minus rate of outflow of momentum plus rate of increase of momentum due to a source. The mass flow is given by m dot, smaller case m. The momentum flow is given by uppercase P dot. Similarly, the law of conservation of energy when it is applied to a control volume is as follows: time rate of accumulation of energy inside an element of the control volume is equal to rate of inflow of energy minus rate of outflow of energy plus rate of increase of energy due to a source. Again, the symbol for representing the energy flow rate is uppercase C dot. I start with the law of conservation of mass, which is applied to the elemental control volume. Here I have taken a two-dimensional control volume, which means its length along the z direction is 1 unit. It has a length along the x-axis horizontal direction delta x. It has a length along the vertical direction delta y. It has a length along the z direction 1 unit. Time rate of accumulation of mass inside an elemental control volume is equal to, first one is rate of inflow of mass. What is rate of inflow of mass inside this control volume? That is given by m dot x, since it is in the x direction, m dot x, m dot y, which is in the y direction. Rate of inflow of mass is m dot x plus m dot y along the positive x direction, that is horizontal direction, along the positive y direction in the vertical direction is shown here. M dot 1 is m dot x, m dot 2 is m dot y. How do you represent it? Using the density of the fluid, velocity of the fluid, and size of the control volume. We know for the x direction, the area is delta y multiplied by 1. The flow is across the surface, which has an area delta y multiplied by 1. So delta y is the area. What is the velocity along the x direction? U, smaller case u. What is the density of the fluid? Rho. Hence, it is the product of density rho multiplied by component of velocity in the horizontal direction, smaller case u, delta y, which is the area perpendicular to the flow in the x direction. Similarly, for the direction along y, density multiplied by component of velocity v, which is in the upward direction, multiplied by area. What is the area? Delta x multiplied by 1. Hence it is simply written as delta x. Okay. Now, what is the rate of outflow of mass? The rate of outflow of mass is written using the rate of inflow of mass and the first order Taylor series expansion. Using the first order Taylor series expansion about the m dot inlets, m dot out along the horizontal direction can be written as mass flow rate at the inlet plus change of mass flow rate with respect to distance along the horizontal direction multiplied by delta x, that is the length of the control volume. M dot x plus partial m dot x upon partial x multiplied by delta x. Similarly, m dot out along the vertical direction can be written using the mass flow rate at the inlet in the vertical direction, m dot y plus change of mass flow rate along the vertical direction, partial m dot y upon partial y multiplied by delta y. Here along the horizontal direction, component of velocity is u. Along the vertical direction, the component of velocity is v. What is the left hand side? Time rate of accumulation of mass inside the elemental control volume. The mass inside the control volume is taken as m, which is equal to the product of density rho multiplied by volume. V is the volume. What is that volume? It has distance along x direction, horizontal direction delta x, distance along vertical direction delta y, distance along z direction 1, hence delta x delta y, volume. So that is the change in the mass of the fluid inside the control volume with respect to time. That is the left hand side of the conservation law is equal to time rate at which mass flow enters the control volume, m dot x plus m dot y, minus the time rate at which mass flow leaves the control volume, which we have written using the first order Taylor series expansion, plus the rate of change of mass inside the control volume due to a source. Here we don't consider any source of mass, hence it is equal to 0. Upon simplification, we obtain the equation partial mcv upon partial t plus partial mx upon partial x delta x plus partial my upon partial y delta y is equal to 0. Substituting for the mass of the control volume, which is the product of density, length of the control volume along horizontal direction delta x, length of the control volume along vertical direction delta y, rho delta x delta y. Similarly, m dot x we have already defined, which is the product of density multiplied by component of velocity along horizontal direction u multiplied by area, which is equal to area perpendicular to the flow, partial delta y. Similarly, m dot y is written in terms of density, component of velocity along vertical direction, and distance, length of the control volume along x direction, delta x. Upon simplification again, the partial x, delta x, delta y can be taken common in all the terms, and which is not equal to 0. The product of delta x and delta y is not equal to 0. Hence, partial rho upon partial t plus partial rho u upon partial x plus partial rho v upon partial y is equal to 0. This is the continuity equation for a two-dimensional flow. It is for an unsteady flow. Here the term containing the partial rho upon partial t is not equal to 0, hence it is an unsteady flow. It is a compressible flow, hence since the density is within the differentiation, partial differentiation. It is a two-dimensional flow. It has the flow direction only, the flow takes place only along the xy plane, not along the z direction. Hence it is a two-dimensional flow. Next, I arrive at the momentum equations for the given control volume. For arriving at the momentum equation, the entire control volume is, the two-dimensional control volume is denoted by four different sides. Bottom side is shown as south for S, left side is shown as west for W, upper side is shown as north for N, right side is shown as east for E. Velocity of this control volume is V. Mass flow entering the control volume is m dot x along horizontal direction, m dot y along vertical direction. Length of the control volume along the horizontal direction is delta x, along the vertical direction delta y. The direction of x and y are shown here. The velocity directions, component velocities, u along x direction, the unit vector is I, v along small case v along vertical direction, the unit vector is j. The momentum of the control volume is uppercase P CV, which is the rate of change of this momentum is shown here is equal to partial mCV u upon partial t into I along the x direction. Along the y direction it can be taken as mCV upon partial t v j. P dot x along west direction, west side is shown by white line, white arrow. P dot y on the west side is shown by green arrow upwards. The P dot x, that momentum is flowing in the horizontal direction due to the mass flow in the west side. The momentum flow in the vertical direction due to the mass flow in the west side is given by P dot y. Similarly, P dot y S, P dot x S, P dot x N, P dot y N, P dot x E, P dot y E can be defined. The force acting on the control volume is shown by F, vector F, which has components along horizontal direction Fx, vertical direction Fy. P dot x, that is the rate of momentum flow along the x direction on the west side is m dot x into u, that is due to the mass flow rate of x direction, horizontal mass flow rate at the inlet, m dot x u. M dot x already we have seen is equal to rho u delta y, hence it is rho u delta y u. It can be written as rho u delta y. P dot y w, that is momentum flow in the west wall of the control volume due to the mass flow in the x direction, m dot x is m dot x v. Using the definition for m dot x, it is written as rho u v delta y. Momentum flow in the x direction on the south wall due to the mass flow in the vertical direction, m dot y u. It is rho v u delta x. Similarly, momentum flow in the vertical direction due to the mass flow in the vertical direction, m dot y v. It is given by the product of rho v delta x. These are the momentum flow which are entering into the control volume. P dot x w, P dot y w, P dot x s, P dot y s. Using this momentum inflow into the control volume, momentum outflow, these are the two sides, west side and south side, through which momentum is entering into the control volume. These are the two sides, north side and east side, through which momentum is leaving the control volume. Next, we are going to find out the momentum flow through the east wall and north wall. To find out the momentum flow through the east wall and north wall, we use the momentum flow which are entering through the west wall and south wall and first order Taylor series expansion. We use the first order Taylor series expansion to find out the momentum outflow using momentum inflow. For example, the momentum flow along the x direction in the east wall, that is shown by white colored characters. P dot x E is equal to P dot x W, that is the momentum flow along the x direction in the west wall, plus change of momentum with respect to change of x multiplied by delta x. That is the first order Taylor series expansion. Already we have defined the momentum inflow along x direction on the west wall is given by rho u delta y plus partial upon partial x rho u delta y into delta x. Similarly, the momentum flow in the y direction on the east wall is written using the momentum flow in the y direction on the west wall with the first law of first order Taylor series expansion as shown here. Momentum flow in the x direction in the north wall, momentum flow in the y direction in the north wall are written using first order Taylor series expansion and momentum inflow rates, corresponding momentum inflow rates. Now the momentum time rate of change of momentum of the control volume P dot CV, as I have already told, MCV is the mass of the fluid contained in the control volume, which has the components of velocity u along x direction for which the unit vector is I, v along y direction for which the unit vector is j. So mass multiplied by velocity will give the momentum. Time rate of momentum, that is partial of mcv u upon partial t. This is the rate of change of momentum of the control volume along the x direction. mcv v, that is the momentum of the control volume in the y direction. Partial mcv v upon partial t will give the rate of change of momentum of the control volume in the y direction. They are shown with their unit vectors I and j respectively. Now, as per the momentum conservation law, rate of accumulation of momentum inside a control volume, which is the P dot CV. Rate of inflow of momentum is through the west side and south side. Rate of outflow of momentum are through the north side and east side. We have written using first order Taylor series expansion and inflow momentum rates, corresponding inflow momentum rates. Rate of increase of momentum due to a source, that is due to a force which acts on the control volume. Hence, using this law of conservation of momentum, P dot CV, that is time rate of change of momentum of the control volume with respect to inside the control volume. This is a vector. Rate of inflow of momentum through the west wall and south wall along the x direction, y direction are shown here, minus rate of outflow of momentum through the north wall and east wall along the x direction and y direction are shown here, plus rate of change of momentum of control volume due to a source, that is due to a force. Here everything is shown by vector sign. Okay, all these quantities are vector quantities. Now these quantities are now written using the variables density, components of velocity and size of the control volume. As we have already seen, the mass of the control volume is density multiplied by volume, where volume is delta x delta y. Along the z direction we have unit volume, unit distance. It's a two-dimensional control volume. Hence rho multiplied by delta x delta y is the mass of the control volume multiplied by u, which will give the momentum along the x direction. Partial of these quantities gives rate of change of momentum with respect to time along the x direction, hence it is having an unit vector I. Similarly, for the y direction it is having unit vector j. Rate of inflow of momentum already we have seen for the south side and west side. Along the west side, rho u delta y. Along the x direction, in the y direction, rho u v delta y. Using these quantities here, written here, rho u delta y, rho u v delta y, rho v u delta x, rho v v delta x. The corresponding direction is also given. Since P dot x is along x direction, it has an unit vector I. P dot y is having y direction, it is having unit vector j. P dot x is again unit vector I. P dot y is having unit vector j. Similarly, the rate of outflow of momentum through the south, east wall and north wall are shown here using Taylor series expansion with the unit vector signs indicating their directions, plus Fx, smaller case f, indicate the force per unit volume in x coordinate direction. Fy is the force per unit volume in the y coordinate direction. Volume is equal to delta x delta y. Hence, we multiply Fx delta x delta y, Fy delta x delta y to find out the net force acting on the control volume in the x direction and y direction with their respective unit vectors. So it is a vector equation. From this vector equation, we extract the momentum equation along the x direction. What we do, the coefficients of the unit vector I are separated both on the left hand side and right hand side. Partial upon partial t, rho delta x delta y u is equal to rho u delta y plus rho v u delta x, such that rho u delta y, rho v u delta x, and so on. In all these terms, after simplifications, delta x delta y is common, which can be taken outside, the product of which is not equal to 0, hence the remaining equation is shown here after removing delta x delta y on both the sides. We obtain the simplified form of equation as shown here. Partial rho u upon partial t, partial rho u upon partial x, partial rho vu upon partial y is equal to fx. This is the x momentum equation. Similarly, the y momentum equation is arrived by extracting the coefficients of the unit vector j in that original vector equation. Now, the x momentum equation is written first, y momentum equation is written second. The x momentum equation is now expanded. Now I make a differentiation of a product. Rho and u are products which can be written as rho partial u upon partial t plus u partial rho upon partial t. Similarly, rho u is taken as a element and u is another element. We make the differentiation of product rho u partial u upon partial x plus u partial rho u upon partial x. Similarly, rho v is taken as an element, u is a separate element, u partial rho v upon partial y plus rho v partial u upon partial y is equal to f of fx. If you see, the rho is present in three terms, 1, 2, 3. These three terms are written separately where rho is common. In other three terms, u is common. U. Okay. We know from the continuity equation partial rho upon partial t plus partial rho u upon partial x plus partial rho v upon partial y is equal to 0. Hence, this term is 0. U multiplied by 0 is 0. So, by applying the continuity equation for this in this momentum equation, we obtain another simplified equation where rho partial u upon partial t plus u partial u upon partial x plus v partial u upon partial y is equal to f of x. So, this equation satisfies both the momentum conservation law and mass conservation law. Similarly, the y momentum equation is simplified using the continuity equation as shown here. Rho partial v upon partial t plus u partial v upon partial x plus v partial v upon partial y is equal to fy. Next, force analysis. In order to find the fluid forces that act on the fluid flow boundary phases, it is required to determine the distribution of stress on these boundary phases. After determining the stress distribution is integrated to find the fluid forces acting on the boundary of the control volume. So, the force analysis is done by finding the stress distribution. The nature of stress acting on a fluid particle. In this control volume, where V is the control volume, which is surrounded by surfaces. Surface is a vector quantity, whereas volume is a scalar quantity. We have a fluid particle P, which is on the surface. This fluid particle is subjected to two kinds of forces. We have the fluid particles both on the surface and inside the control volume. I talk about the fluid particle which is on the surface of this control volume P, which is acted upon by two kinds of forces. The first kind of force is experienced by on the surface of the fluid particle per unit area of the surface, called stress. It is called stress. Another force is experienced by the entire volume of the fluid particle per unit mass of the fluid particle, called specific body force, FB. The fluid inside that control volume V is enclosed by the surface S at a point P on the surface ds. On the point P on the surface ds, where the unit normal is N, the stress is sigma. This is the first kind of force, the force experienced by the fluid particle on the surface of the fluid particle. At a point volume, this is the point volume which has a volume dV. The density is rho and the specific body force is Fb. This is the second kind of the force which is acted upon the fluid particle. The definitions of the various symbols are given here. Rho is density, dV is elemental volume, P is the fluid particle, V is the volume of the domain, fluid domain, S, vector S is the surface area of the fluid domain, ds is the elemental surface which encloses the fluid particle P. The stress, the first kind of the force, arises between the molecules on the surface of the fluid particle and the molecules outside the fluid particle. This force depends on the relative motion of the molecules and the relative position of the molecules. The stress has two components, a component sigma n, which acts normal to the surface of the fluid particle, called normal stress, a component which acts tangential to the surface of the fluid particle, that is tangential or shear stress. As shown here, a normal component of the stress sigma n and tangential component of the stress sigma t. So this state of the stress at the point P, that is the fluid particle. The fluid particle is represented by point P. It is described by two components of the stresses, stress vector, for each of the two orientations of the given surface, ds. So the ds surface has one horizontal orientation of the surface, for which the two components are sigma yx, sigma yy. Another vertical component of vertical orientation of the ds, that is having the two components sigma xx and sigma xy. These are the two components of the stress vector sigma for each of the two orientations of the given surface ds. So the ds is the elemental surface that encloses the fluid particle represented by point P. For this elemental surface, there are two orientations of the surfaces: horizontal orientation surface, vertical orientation surface. In the horizontal orientation surface, there are two components of the stress vector, and for the vertical orientation of the surface, two components of the stress vector. Combinedly, these four stress vectors define the state of the stress at point P, that is sigma xx, sigma xy, sigma yx and sigma yi. These four quantities define, these are the vector quantities shown by overbar, define the state of the stress at the point P. Sigma ij, you see here I can be x or y here. The first letter I refers to the direction of the surface normal. For example, in the sigma xx, the normal direction is perpendicular to the vertical line, that is along the x direction. Hence, the first letter is x. Here also the first letter is x. What about here? The surface is horizontal, so the surface normal is along the y direction. Hence, the first letter is given by y. So the first letter in the stress vector refers to the direction of the surface normal. The second letter, that is index, refers to the direction of the force component. You see here sigma xx, the second index is along showing x, that is the force is along the x direction. In the sigma xy, which is a tangential stress, the force is along the y direction, vertical direction. The x direction and y direction are shown here. Positive x direction, positive y direction, negative x direction, negative y direction. Similarly, on this surface, the second index x indicates the direction of the force, that is along the x direction. Y indicates it is the direction of the force, vertical direction. Now, the entire control volume, which has delta x length along the x direction, delta y length along the y direction, 1 unit length along the z direction, has a point P inside of the control volume, which may also be on the surface of the control volume. On that point, the state of the stress is shown by these four stress components: sigma xx, sigma xy, sigma yy, sigma yx. Using these four stress components, the net force in the east side of the control volume, west side of the control volume, south side of the control volume, north side of the control volume are given by F1, F2, F3, F4, F5, F6, F7, F8. One force is acting normal to the surface, that is normal due to the normal component of the stress vector. Another force is acting tangential to the surface, which is a tangential stress component or shear stress component. These components F1, F2, F3, F4, F5, F6 are shown here. For example, F1. How can you write F1 using the state of the stress at the point P inside the control volume? Sigma xx plus. Why it is sigma xx? The F1 is along the x direction. Hence, the force is along the x direction. Sigma xx. And the surface normal is also along x direction. Hence, sigma xx. Using the first order Taylor series expansion, sigma xx plus change in sigma xx with respect to change in x. What is the distance between this point, which is at the center of the control volume, to the east face of the control volume, delta x by 2? Because the total length of the control volume along the horizontal direction is delta x. So delta x by 2. This is indicating the stress acting on the east face of the control volume. How to find out the force? We have to multiply by area of the surface. Area of the surface perpendicular to the stress component. Delta y is the length along the vertical direction multiplied by delta z is equal to 1. This is the stress multiplied by area will give the force. If you divide by the delta V, which is the volume of this fluid domain, then it is given by sigma xx plus partial sigma xx upon partial x delta x by 2 multiplied by delta y upon delta v. Similarly, the F2, where the force is along the y direction, so the second index indicates the direction of the force. The first index indicates the direction normal. This force is acting on the surface which has a normal in the x direction, hence sigma xy. Using Taylor series expansion, first order Taylor series expansion, it is written. Similarly, F3, F4, F5, F6, F7, F8 can be written. Whereas the forces on the east side and north side are given plus sign. The forces on the west side and the south side are given minus sign, because with respect to the state of the stress at the point P, which is at the center of the control volume, this F3 force, F4, F8, F7 are acting at the points which are to the left side. Hence, they are given minus sign. Gx and Gy are the body forces in the x and y directions respectively. Now, the net force per unit volume acting on the x direction due to the body force Gx and the surface forces F1, F3, F6 and F5 are written here. F1 is along the positive direction, plus x direction. F3 is along the negative direction, negative x, that is why minus F3. F6 is along the positive x direction, plus F6. F8 is along the minus x direction, hence minus F8. The plus x, plus y, minus x, minus y directions are shown here. The Gx is the body force per unit, body force acting on the control volume. It is the product of density multiplied by volume, which will give the mass of the control volume, multiplied by acceleration due to gravity component along the x direction, Gx, mg. Already we have seen F1, F3, F6, F8 in terms of the stress vector components, sigma xx, sigma xy. So we substitute these quantities here. Upon simplification, we obtain the equation here, which is shown at the bottom. Fx is equal to rho gx plus partial sigma xx upon partial x plus partial sigma yx upon partial y. Similarly, the force component along the y direction, that is per unit volume, can be written using the body force component Gy, surface force components F2, F4, F5 and F7, which is shown here. Fy is equal to rho Gy plus partial sigma xy upon partial x plus partial sigma yy upon partial y. Now, we have written here the x momentum equation, where Fx is the force per unit volume acting on the x direction of the control volume. Fy is the force acting on the control volume in the y direction per unit volume, using the quantities on the left hand side, which are due to the inertia forces. The equation of x momentum is shown here. So the left hand side indicates the inertia forces, which we have arrived separately using momentum flow inlet, momentum flow outlet, and the right hand side indicates the net force acting on the control volume, that is the momentum flow, rate of change of momentum due to a source, that is due to the force. The first term on the right hand side is due to the body force. The remaining two terms are due to the surface forces. Similarly, y momentum equation is written using inertia forces, body forces and surface forces. Dynamic viscosity. The definition of dynamic viscosity. Let us take the bottom plate is stationary and the top plate is moving with a velocity v. In between the two plates, there is a fluid having a thickness h. We consider two particles on a line, vertical line, P and Q. The particle P is moving with a velocity small u, smaller case u. The particle Q is moving with a increased velocity u plus partial du upon dy into delta y, because of the movement of the upper plate. At any time, the distance by which the Q has travelled is more than the distance travelled by P. The difference in the distance is shown by the lines Q, Q dash, P, P dash. So the shear strain, which is shown here as delta phi, is equal to the difference of the distance travelled by Q and the distance travelled by P divided by the vertical distance from P to Q. It is also called time rate of shear strain, E dot, which is the ratio of this with respect to time. Rate of change of this strain, shear strain with respect to time, where limit delta t tends to 0. We know from the definition what is length of Q, Q dash, u plus du by dy into delta y multiplied by delta t. This is the distance travelled, okay, this is the velocity multiplied by the time will give the distance travelled by the point Q. This is the distance travelled by the point P. The difference between the two distances divided by the vertical distance between the 2 points, delta y. When delta t tends to 0, it becomes equal to du by dy. So the Newton's law of viscosity states that the stress, shear stress in a fluid flow is proportional to rate of shear strain, time rate of shear strain. The constant of proportionality is called viscosity. So here the flow is taking place in the xy plane. We have a tangential stress called yx. What is the first letter indicates y? It has a unit normal perpendicular to the area, and the second letter indicates the direction of the force. The direction of the force is in the x direction. So So the tangential shear stress on a surface which is oriented along x direction is given by mu du by dy. Similarly, sigma xy can be written as mu dv by dx. When the fluid element is moving due to the fluid flow, it is subjected to three kinds of motion: translation, that is the motion along the straight line; rotation, that is about a point, it is moving along a curve. It also has deformation. Here the fluid element, which is initially having delta x length, delta y length, deforms into a bigger element, elongation, in both x direction and y direction. Volume change. What is the final distance between the points A and B? Delta x plus u, which is the velocity of the fluid particle at point A. So the distance travelled by the A is u delta t. What is the distance travelled by B? The velocity of the B is written here using the first order Taylor series expansion and the velocity of u at point A, u plus du by dx into delta x, multiplied by delta t. Delta t is the time duration in between which the fluid element passes from this location to this location. So u plus du by dt dx delta x into delta t. Using this strain, rate of strain along x direction is written here, where it is written in terms of delta t, ratio of delta t. Change in length along the horizontal direction divided by original length. Similarly, rate of strain, linear strain in the y direction can be arrived at, which is partial v upon partial y. So this partial epsilon, this epsilon dot xx, epsilon dot fy are the rate of strain due to the translation motion of the translation and deformation of the fluid particle. Then we also have the fluid motion, which has a rotational motion. Initially the fluid element is horizontal, is square in shape. Upon rotation it becomes a rhomboidal shape. The side AB has not only increased in length from AB to A double dash B double dash, but also has rotated by an angle delta alpha. The side AC has rotated about delta beta. The delta alpha is the angle, that is vertical side is B dash B double dash, horizontal side is A double dash B dash. Using again the velocity components u and v at points A, B, C, D, we can find out delta alpha, which is shown here, partial v upon partial x delta t divided by 1 plus partial u upon partial x delta t. Similarly, delta beta can be written, the total shear deformation due to the rotation of the fluid element is shown here, which is delta alpha plus delta beta. Using the time rate of shear strain, the shear stress can be defined using the Newton's law of viscosity. Sigma xy is equal to sigma yx is equal to mu partial v upon partial x plus mu partial u upon partial y. So the normal stress sigma xx can be written using this equation, where the first one indicates the stress due to pressure, the second one indicates the stress due to linear deformation. Dynamic viscosity mu is called first coefficient of viscosity. and using the second coefficient of viscosity lambda partial epsilon dot xx plus epsilon dot yy. Similarly, sigma yy can be written using the velocity components. We write again this normal stress sigma xx and sigma yy. Now the x momentum equation can be written using the components of velocity u and v as shown here, where the sigma xx and sigma yx are replaced with the component velocities and gradient of velocities, partial u upon partial x, partial v upon partial y. Upon simplification, we obtain an equation as shown here. The red underlined term is called time rate of change of momentum of fluid element having unit volume in the x coordinate direction. The yellow underlined terms indicates the time rate of change of momentum of fluid element having unit volume due to motion of the fluid element through the space. It is called advection component. The first one is called unsteady state component, second two terms are advection components. The green underlined term is the force due to the gravity, body force. The blue one is the force due to the pressure. The maroon colored one is the sum of the terms underlined by maroon color is called the force due to the viscous effects. Rho gx, that is the net force acting on unit volume of the fluid element due to the gravity or body force, minus partial p upon partial x is the net force per unit volume due to the pressure in the x direction. The remaining terms, sum of the remaining terms are the net force per unit volume due to the viscous effect along the x direction. Similarly, the y component of the momentum equation can be written using the velocity gradients. Finally, I write the x momentum equation, y momentum, I summarize the x momentum equation and y momentum equation and continuity equation for an unsteady flow, for a compressible flow, for a two-dimensional flow. So these are the x momentum equation, y momentum equation and continuity equation for compressible, two-dimensional and unsteady flow conditions. With this I conclude the lecture 1 of the series of talks on computational fluid dynamics and heat transfer. I shall meet once again during the next lecture 2 on computational fluid dynamics and heat transfer. Thank you.